There, so I don't forget. How are you?
Oh, pretty good.
Good. How was your Model UN?
Oh, I guess it was pretty exciting. It was my
Uh-huh.
last one, so
Oh,
yeah.
so did you represent our great country well?
I thought I did a pretty good job.
Yeah, I bet you did. Ryan Logan, can you hear me? Oh, they're not. I don't think they're plugged in yet.
Can you hear
Oh,
us?
yeah.
Yeah, now we can.
Okay, great. It was muted.
All right, good. Um, okay. So I sent you guys email. You got that, right? Or if you
Yeah.
didn't, then look at it. Okay. Because yeah, that's the first thing I want to say is yeah, is when I told you when this stuff is due. Um, and Walter, I don't think I got your assignment yet, right? Is that right?
Yeah, I was preparing for the AMC this morning. So
Oh, the AMC was today? Or
yeah.
Yeah. Yeah.
wow. Oh, wow. Heavy. How'd you do? You don't know.
Um. I think if I didn't make any mistakes, I think I got like a 117, but
Wow. That would be awesome.
Oh my.
Yeah, okay. Now you know. Have you guys taken Ryan Logan, have you taken that?
Yeah, we
Yeah.
took it today.
Oh, you take it. Oh, you haven't taken it yet.
No, we took it today.
Yeah, we
Yeah.
just
Oh,
took
you
it
also.
like 30 minutes ago. Yeah.
Yeah, I can't
Oh,
say I
wow.
did the
The best.
can't
Yeah.
say I did as well as Walter at all.
Yeah.
Yeah. Well, Walter's, yeah. Enough said. Okay, the other thing I want to say is I put your grades on eCollege. They're not weighted yet. So I want to make sure you can see them. Um, so why don't you try that? Go to eCollege, and then if you go to the grade book and click on your name, you should be able to see it. I just want to make sure you can.
Okay. I can see the grades.
I can
Excellent.
too.
Okay, good. We're good. Um, okay. So basically, I'm giving full credit for homework and class participation. Even if you weren't in a class, it's too hard to, so if you're absent, you just get full credit. Um, but in the future, you
I
know,
think they put in
you may not get
he emailed me until today.
you may not get full credit if you don't, you know, turn in your homework on time or get or not participate in class. And I also want to I don't expect that to happen, but I'll just throw it out there. And then I want to encourage you once again to communicate with each other. You now have each other's email, right? And you have mine,
Mhm.
yes? So,
Yeah.
if you're confused about something or something's not, clear, you have a question or you want to work together, that's wonderful. And that's how mathematicians work. The Renaissance person who does everything himself uh, or herself. That happens, but it's very rare. Andrew Weil did that for about 7 years when he was working on proof of Fermat's last theorem. He mostly kept it to himself, but that's the exception. It's not the rule. Most people really, scientists, everybody these days, you have to work with other folks. Okay. while I'm doing this, you should go into the Tuesday class of Adobe Connect if you haven't. And I'm just going to share my screen here. Hopefully it will work this time. Yeah. Okay. That's what I should get. And I'm sharing the main display, right? All right. So the reason I'm doing that is just to show you briefly the topic list. And I got feedback from Logan. Thank you, Logan.
Yeah.
And so I just wanted to show you that where we are. So we're doing more on symmetry today, and we've started this, and we're going to do more on more on 3 and 4, exploring transformational axiom set. Walter was, and I'm big on that too. And then we'll do this quickly. Both Ryan and Logan wanted some stuff on complex numbers, and I know a fair amount about that, and some approaches you may not have seen. So I'd like to do a little on that, and 2 out of 3 ain't bad. And Walter wanted to do the 3D, and the 3D is really interesting. So yeah, so I'm feeling good about doing that. And then geometric probability, there is a nice source that a book from COMAP that I bought electronically, and now I can share it. So I will share that with you, and that also is quick but interesting. And then we'll figure out what to do after that. So I just wanted to quickly do that, and not this yet. So today, what I had in mind was first to use GeoGebra, and I put these sketches on so you guys can share your screens when we do this. I put some sketches in eCollege under February 3rd classwork. And the first one I would like you to open is vertical angles are equal. Vertical angles equal. Maybe at the bottom, but it's there. And I will open it too. Excuse me. Looks like this. So you should see 2 lines that meet at A and a point B on one of them and a point C on the other. And the lines are dashed, I hope.
Mm-hmm.
Okay? All right. I want to, so what we want to do is prove that the vertical angles are equal, the one to the right and the one to the left. But in order to kind of make a good angle that we can move as opposed to measuring an angle, there's a tool I haven't talked about, and I think it's under line. Yes. So if you go under line, which is the third menu from the left, you'll see something called polyline, which is below ray. You see that?
Mm-hmm.
So select that, select polyline. And then if you hover over it, it says select all vertices, then click the first vertex again. And so I think, I didn't try this, I should have, just the order. So I'm going to do B first, then A, then C, and then click B again. So let's try that. B first, then A, then C, and then click B again. Yes. And it's called a polyline because it really makes two segments. So what we've made is the angle CAB. Okay, everybody with me?
Mm-hmm.
Now we want to prove that the vertical angle is equal by doing a transformation. So on the polyline. So I want you to think for a minute. It's not too difficult, but think about what transformation you would use. And I want a complete specification of the transformation. So you can't just say translation. You have to say translation by what vector. So. So this is different from, while you're thinking, this is different from the usual proof, which is when we, we use kind of algebra, supplementary, if one is x, then 180 minus x, and then x, but we're not doing that. We're doing a transformation proof. So who's got a thought? It's okay to be wrong.
You can rotate. Sorry, you can rotate the polyline, I guess, CAB.
Yeah.
Around A by 180 degrees.
Okay. What do Logan, Ryan? What do you think?
That sounds right.
All right. So do that. Use the rotation tool. And one of you, Walter, why don't you share your screen? And I'll get back to so we can see what's going on. I'm going to close mine so I'm getting away. All right. Meeting is opened and Adobe Connect in. You can now close this window. Oh, I see. Okay. Are you able to do it? Or is it? I closed the window. I'm not sure I should have done that.
I can't share my screen.
Okay. Ryan, can you share yours?
Yeah, can you make me a presenter, though?
Oh, hello. Good morning. Yes. Just a minute. Let me make sure I don't log on twice, first of all. Okay, so I quit that, and now I need to open. I saw advanced math topics, and it got me confused. Give me a second. If I go to history, yeah, here's my, yeah, right. Gosh, so hard to remember all these little details. All right, there we go. That's why you couldn't. Okay, so make presenter, and make presenter. That's why, Walter, that's why you couldn't share it, because I messed up. Okay, so you're all presenters now. So now try. Ryan, why don't you try?
Okay.
There we go. It's happening. There it is. Okay. All right. So you rotated it. Nice. So you rotated it around, and there it is. Okay. Now, why are now this is different reasoning. Why are the angles equal?
Because
let me have somebody else. Logan, can you do it? Why are the angles equal?
Well, rotation preserves angles between points.
Bingo, stop. Perfect. Thank you. Rotation preserves angles, so that's the easy part. But why is the 180 degrees important? I mean, if we rotated through 73 degrees, rotation would preserve angles also. So what's so special about 180?
Well, because the image of B is still on the same line.
Yes, that's the crucial thing. It makes a straight angle, right? 180 degree rotation makes a straight angle. So when you take a ray and you rotate it 180 degrees around the endpoint, you get the opposite ray, which is on the same line. So the two lines are formed. So that's the difference between a transformation proof and a normal, or the usual proof. The usual proof, we know we have lines, and then we show the angles are equal. Here we know the angles are equal when we rotate, but we have to show that we have lines. So it's backwards. Okay? But really nice, and there's no algebra. Okay, that's the first one. Now, let me just tell you a little bit before we do the next. So today we're proving these fairly straightforward things in the beginning. Then we'll do some harder stuff. The parallel postulate, I looked at that, and so I'll just tell you, because Playfair said at most, through any point not on a given line, there's exactly, so for us it's going to be through any point not on a given line, there's exactly one line parallel. But Playfair said at most. And the reason is, let's see. I'm going to request control and share my screen for a minute. I want to show you something interesting. So, yeah, there we go. And now what do I do? So there you go. That's right. Thank you, Ryan. And now I'm sharing my screen. And I am going to open iBook's author, because I downloaded, this is kind of nifty, and I want to open a recent, that's not what I want. Wait a sec. Oh, did I do iBook's author? I don't want that. No, iBooks. That's iBooks. There, that's the one I wanted. Did the wrong one. I downloaded Euclid's Elements, and this is an iBook. There it is. Can you see that? And I'm going to go back. I'm not sharing?
Not yet.
Oh, yeah, that's right, because I didn't get that other. Okay, so let me go back here. I should get that. Yeah, there. I should get that. There we go. Now I should be sharing. I have to go back here. All right. This is Euclid's Elements, and in Euclid's Elements, he tried to. So this is very quick. He tried to avoid using the parallel postulate until he absolutely had to. So, this is kind of interesting. It cost me $6. Not bad. And the diagrams are are dynamic. They move. So this is the business with common notions, and this is his propositions, and this is the way Euclid writes. It's kind of translated, obviously, but it's an interesting style. It's like learning Shakespeare. but it's not hard to read. It's really not hard to read once you get used to it. So prop 4, there are crucial propositions. Proposition 4 is kind of amazing because it's already side angle side congruence. If two triangles have two sides equal to two sides respectively and have the angles contained equal, then they'll also have the base equal to the base. So the third and the triangle will be equal to the triangle. That's what he meant by them being congruent. And the remaining angles will be equal. So that's sine angle side congruence. That's one important thing he does right early on. And then Prop 16 on this. Prop 16 is a very interesting one because this is without knowing that a triangle has 180 degrees. It says, in any triangle, if one of the sides be produced, in other words, extended, the exterior angle is greater than either of the interior and opposite angles. Okay? And the way he does it is pretty interesting. So I'm pointing to this diagram. Here's a triangle, and he takes the midpoint, E is the midpoint here, draws a segment from B to E, extends it an equal length out to F. So BE is equal to EF, and since E is the midpoint, AE is equal to EC, and because vertical angles are equal, the included angles are equal, so the triangles are congruent, so the red marked angles are equal. But then he uses from the diagram that clearly the exterior angle is bigger than this red angle here. So the exterior angle at C is bigger than the angle at E. You remember what an exterior angle is? You extend the line, extend one of the sides, and it's between the adjacent side and that extension. So that's what he does in Prop 16. With me? One more. And then the interesting part, so say something. Are you okay so far?
Yeah.
Okay.
Yeah.
Yes, Ryan? Yes, Logan?
So he's talking about angle FCD.
He's talking about angle, no, the exterior angle is, thank you for asking, thank you. The exterior angle is ACD.
Okay.
Because it's what happens when you extend a line and use the adjacent side of the triangle. So the exterior angle is ACD. And he's proving that ACD is bigger than angle A. Bigger than the non-adjacent. The adjacent one would be here at C. The adjacent one would be BCA. But the non-adjacent ones are A or ABC. Those are the non-adjacent ones. And he's showing that ACD, angle ACD, is bigger than angle A. Okay?
That makes sense.
Yeah. Good.
Yeah.
All right. Now, why in the world would you do that? And the reason is Prop 27, and this relates to the confusion that that Walter and I had when we were talking about Playfair, and this is the idea about at most. So Prop 27 says if a straight line falling on two straight lines, that's what we call a transversal. So if you have a transversal and it makes alternate angles, he didn't say interior, alternate interior angles equal to each other, then the lines are parallel. So he proves that without the parallel postulate. If the alternate interior angles are equal, then the lines are parallel. What you can't prove without the parallel postulate is the other way around. If parallel, then the alternate interior angles are equal. Okay, but you can prove this without anything else. There could be more than one parallel. But that's why, so you can always make a parallel by making alternate interior angles equal, and then you have the parallel. So you can make a parallel in what they call neutral geometry. Neutral means without the parallel postulate. Okay? And there are other geometries which satisfy everything except the parallel postulate, and we're going to talk about those later. So there's always at least one parallel in this neutral geometry. But that's why Playfair had to say at most one. And there is, optionally I'll put it, there's a proof online that I looked at about the equivalence of of Euclid's fifth postulate, which is if two angles are less than two right angles, then they meet on the same side, and at most one parallel line. There's an equivalence between those two things. So the way he proves it is, and I'll post the link to that in an announcement. I haven't done that yet. So here's what he does, and let's just go through this quickly. So, so we're supposing these angles are equal, and we want to prove the lines are parallel. So he says, for the straight lines EF falling on two straight lines, make the alternate interior angles. I say that, so he always starts off with a claim. It's kind of interesting. I say that AB is parallel to CD. This is for if not. So what kind of proof is he doing here? If you say if not.
Contradiction.
Yeah, it's a proof by contradiction or an indirect proof. Right? So suppose it's not true. Then when they're produced, they will meet in the direction of B, of BD, of B and D, which he calls the endpoints of those segments, or towards AC, one of them. It's going to meet on one side or the other. Let them be produced and meet in BD at G. So suppose these lines actually meet here, okay, when we extend it. So you would get a triangle. The triangle would be EGF. Okay? Without reading, can you tell me what the contradiction is? Why can't you have a triangle here with these angles equal? And that's what we just talked about.
You just proved it earlier, right? That the exterior angle is bigger than the interior or the opposite.
Right. The exterior is bigger than this, but so it can't be equal because this would be the opposite. This would be the non-adjacent interior angle. So that's the contradiction. And it's the same thing on the other side. You just have to use this angle instead. So that's why he used the exterior angle. That's why he proved that the exterior angle is bigger than the non-adjacent interior. He hasn't proved that an exterior is equal to the sum of the two, which is Euclidean, which is normal Euclidean geometry with a parallel postulate, but he did prove that it's greater than. Okay, so I just wanted to go through that quickly. Now, let's go on to proving, oh yeah, and I have to say one more thing. I've been thinking about you know, the parallel postulate and all that stuff and what it is. And I think we have to make an assumption in our geometry about translation. And I think the assumption we have to make is that translation preserves direction, which is a fairly obvious thing for us, but not true. I don't think, I don't know, but I don't think that will be true in these other geometries. In fact, I'm not even sure when we get to it how to define translation in these other geometries. For example, suppose you're on a sphere. If you're on a sphere, then lines are great circles. And that's one kind of geometry that we'll deal with. And lines are great circles. In that case, you have no parallels, which is kind of interesting. But how do you define? You define rotation is pretty easy, I think. If you have two great circles meeting at a point, you can still rotate them around. You know, two lines on the surface of the Earth that are great circles, you can rotate them. I think you can reflect just by going on the other side that that's a fairly straightforward concept. I don't know about translation. I'm not sure how you would define translation on a sphere to get one great circle to go into another great circle. So I think translation is the thing that breaks down. So that's my conjecture. I haven't proved that, but I think we have to assume that translation preserves direction. So I'm going to add that to our assumption list, unless one of you can prove it. And a more careful restatement of it is going to be the image of a line under translation, but the translation has to be along a vector that's not parallel to the given line, right? You can't translate a line along itself. But if you have any other translation, then the image line will be parallel to the pre-image line. Okay. Now, with that in mind, we're ready to go to the next GeoGebra. Next GeoGebra, so I'll close this. And we're going to open in GeoGebra, watch my time. Yeah, I'm doing all right. We're going to open parallel, yeah, the one that says, so here I'm going to open the one that says parallel implies corresponding. And Logan, I'd like you to share your screen if you would.
Yeah.
So I have to relinquish control, I think. Just a minute. Close that. And you get here. What happened to my? All right, wait a second. This is eCollege. Yeah, that's not what I want. I lost it. So let me get it again. Advanced Math Topics Tuesday. There we go. Okay, give me a second. Oh, now I got the same. Sorry. I hate that. I made that same stupid mistake. All right, I'm gonna close Chrome entirely here. Get rid of all that stuff. Oh, Adobe Connect. I have to. Oh, I hate making this mistake. All right, I have to quit this. There we go. Okay. Now I'm on just once. Okay. All right. So it should be all right now because I'm on just once. So Logan, can you share your screen?
It says I'm downloading the plugin, which I already have.
Oh.
Okay, cancel. No, please. No, please.
You know, it'll pop up.
Okay.
Get under that thing.
Yeah.
There you go.
Oh, okay, cool.
It should just
Okay.
There you go.
Okay. Yeah.
We're getting better at this. We have to work our way through it. I'm having my trouble too. When I share my screen, Adobe Connect opens.
Is it working?
Wait, let me check.
Yeah, that's good. And now you want to yeah, that's right. You want to get that GeoGebra file. There it is. Okay. Thank you. Great. All right. So we're assuming parallel. So we have the red line L and the blue line M, and we're assuming they're parallel. And we want to prove that the corresponding angles are equal. So make a polyline by clicking C first, and then P, and then B, and then C again. Okay, there's your polyline. Now, what transformation do we want to do to that polyline? Yeah, you can mess with it.
Yeah, I can't really see it too well.
You can make it thicker too if you go to Style after you, see this?
Yeah.
Yeah, you can move that up to like 4. That's what I do. Yeah. Nice. Good. Okay, what transformation do we want to do to that polyline in order to show that the corresponding angles are equal? Logan, can you tell me?
You translate and rotate it?
Corresponding angles. You know what the corresponding angles are?
C, Q,
Just point to it. Put your mouse where the corresponding angle is.
Yeah, it's C, Q, and this line.
That's the alternate interior angle. That's the on the other side. Corresponding, think about corresponding. This is now in the upper right on the bottom, right? Between the line and the transversal?
Yeah.
Okay. So where's the corresponding one with the blue line? Just move your mouse to where it is.
Just be CPB?
CPB is that one, but I want the corresponding one with the blue line and the transversal. with M in the transversal. Where would that be?
Oh,
Yes, right there, right there, right there.
yeah, okay.
Yes, that's the corresponding angle. Right. Now, what transformation would we have to do to angle CPB to move it up there?
A translation.
Good. And in order to do a translation, what do we need to specify a translation?
A vector quantity,
Right.
I think.
So you need to make a vector. So go to the polyline area and select vector. And you have to select the initial point and the final point. Yeah. Excellent. Now go to translation. Very good. And translate that polyline by that vector.
Got it.
There it is. Okay. Now let's look at that new angle, which is C prime GB. Okay? All right. How do we know that the angles are equal? 3 words.
Isometry preserves.
Translation preserves angle measure.
Good. So we know the angles are equal. That's no problem. How do we know that C prime Q lies along the line? That's not somewhere different, that it's not off the line. How come it has to lie along the line, the transversal line?
It's because the vector is in the same direction as the line.
Yes, exactly, because the vector is along the line. So that part's easy. Now, here's the part that I wrestled with. How do we know that QB prime lies along line M, which is a parallel line?
Well, M and L are parallel.
Yes.
And PB and QB prime are parallel also.
Right.
And
So translation has to map a line into a parallel line. That's where we need the assumption, right?
Yeah.
That's where we need the assumption that translation preserves direction. And I don't think there's a way around that. I think we need to make that assumption. I'm just discovering this along with you. I was messing with this. Okay. All right. Good. Now let's do the converse. Ryan, can you do the converse? So I want you to relinquish. I don't know if Logan, do you have to relinquish control?
yeah, I think
Yeah.
so.
And then Ryan, you get control.
Got it.
Share your screen.
You just stop sharing.
Sweet.
Okay. And then close that one and open the one that's the other way around. Corresponding implies parallel. Okay. Now in this one, I labeled, so I have 2 lines. We don't know they're parallel. Okay? But I labeled the angles A alpha for the bottom one, and I couldn't label the top one alpha. It wouldn't let me. So I labeled it alpha 1.
Okay.
So we know those angles are equal. And we have to prove that the lines are parallel. So it's similar to before, but slightly different. So think about how you would do that.
Would I have to use the interior adjacent angle? Or,
No, you don't,
That-
have to use, you don't have to use any other angle. It's very similar to the previous, except we have to state things in a slightly different way.
okay.
We know the angles are equal. So what transformation are we going to use from the bottom angle to the top angle? This is really similar.
Just a translation?
Yeah, the same translation. So we take that, and you don't have to do it. You don't have to do it. Just watch. Yeah. So right. So that's right. Thank you. So just look at the bottom angle, okay, and we're going to translate it by that vector, right? So what do we know? We know that angle. We know that the transversal remains fixed.
Mm-hmm.
Okay, and we know that translation preserves angles. So the image of PB has to lie along line M.
Mm-hmm.
Because the angles are equal, right? Otherwise, it would lie somewhere else.
Yeah.
Okay. But what do we know about translation and angles and direction? By our assumption
that it preserves angles.
that it preserves angles, but we also made an assumption, and the assumption was that it preserves what else besides angles?
Distance.
Yes, but what else did we just make? That crucial assumption that we just used.
Oh, parallelism.
Yeah, that it preserves direction. So the image has to be parallel if we do a translation, and it has to be the same line as the one. Because the angles are equal, it has to be the same line, and because translation preserves direction, it has to point in the same direction. So that image line really will be parallel. So if the corresponding angles are equal, then the lines are parallel. So we went both ways.
Okay.
It's subtle, but it's more or less the same. So with that assumption, that powerful assumption gives us the parallel postulate, basically, both ways. And then, of course, if you have corresponding angles, then alternate interior angles, which means alternate interior means between the parallel lines, between, and alternate means on opposite sides of the transversal. I'm reminding you of your geometry from years and years and years and years ago. Right? Okay. So after we get corresponding, you can get everything else. And you could get the alternate interior angles directly. I'm gonna put that as a challenge. Okay. Well, we're gonna do that in a minute, so we don't need that. Okay, Walter, your turn. Ryan, can you relinquish? Yeah, and Walter, can you share now? I made you a presenter, so you should be able to.
Okay.
Yeah, you're a presenter. Yeah, you're under presenter. Let's see if Walter's connection is sometimes a little weak. So, are you able to do it, Walter? Or are you having trouble?
No, I'm
Okay.
having trouble.
All right, I'll do it. I'll share mine, and I'm not gonna mess up this time, I hope. All right, so I am gonna open GeoGebra, and hopefully you can see. Oh no, it didn't. I'm gonna have to do it again because it has to give me that. There it is. Sometimes it doesn't work the first time. I'm realizing. Share. Okay, it has to give me that screen where it says share. Otherwise, it's not working. Okay, so here's GeoGebra. This is the last one, and I also showed it to you. So I'm going to open the one that says triangle angle theorems. So now we're ready. This is the question that Ryan asked me last time. Can we assume that the sum of the angles of a triangle is 180? And that does not work in these other geometries, in these non-Euclidean geometries. That's what they're called. So I have made this diagram. Can you see this?
Mm-hmm.
All right.
Yes.
So we have the original triangle, which is, and I've labeled the angles alpha, beta, and gamma. And the original triangles are usual orange. Okay? And then I did a transformation, an isometry, to make the indigo, the image triangle. And what transformation did I do, Walter? How did I get the orange one onto the indigo one?
Wait,
Not sure?
Well, like, is it one transformation?
One transformation.
Alright, did you do a glide reflection?
No. Good try. Ryan, Logan, do you have an idea?
Did you rotate it around the or rotate the orange triangle around the midpoint of that line? Yeah.
Side, yes, yes. I rotated around this midpoint. Right, exactly. By how many degrees?
180.
Right. So, so since I did a 180-degree rotation, this side is going to line up with itself because that's a straight angle. Right?
Mm-hmm.
Okay. And beta is going to equal beta prime because, 3 words.
Rotation preserves angles.
Perfect. I love this. Right. So these angles are equal. These are alternate interior, right? Mm-hmm. So this left-hand side of this triangle, I guess I should have labeled the vertices, but this left-hand side between angle alpha and angle beta is going to be parallel to this here, right? Similarly, gamma here is equal to this angle up here because rotation preserves angles. And so this is now a parallelogram. The opposite sides are parallel, at least by the opposite sides are parallel, let's just say that. We're going to make a different definition for a parallelogram shortly. But the opposite sides are parallel here, okay? All right. Now, beta prime is, of course, equal to beta because, all right, now, how did I get from the orange triangle to the green triangle? Walter, how did I do that?
Yeah, you translated it by, yeah, that vector.
Yeah, this vector here. So I translated it. So that means alpha is equal to alpha prime here. Yes?
Yeah.
Okay, so now we have 2 theorems staring us in the face. What's one theorem?
Corresponding angles are equal.
Yeah, but what about, this is triangle theorems.
All the angles of a triangle make a straight angle?
Yes. Here's the straight angle. Right? Alpha plus beta plus gamma is equal to 180 degrees. There it is. So now we can use that. The sum of the angles of a triangle is 180. We have another theorem, which has the word exterior in it.
The exterior angle is the sum of the 2 opposite angles.
Yeah, 2 opposite interior angles. See, alpha plus beta here is equal to alpha plus beta here. So the exterior angle of a triangle is the sum of the 2 opposite interior angles. So there they are in one diagram. Done. Okay? So we answered, Ryan, we answered your question. Now you can use it. Okay? Now, I'm not going over the HL congruence today. You do not have to use that for HL congruence. All right? But next time, I want one of you guys to share your proof. And we'll go through it. And I'll say once again, that mistakes are gifts. It's okay to not get it right the first time. All right, one more thing to do today, and I want you guys to open this document also. I'll continue to share my screen. I'm going to close GeoGebra. And the document is also in eCollege, and part of it is going to be for homework. And it's called Symmetry Definitions and Proofs. So open that, and we're going to start working on it. And you can do the work on your document also, because this is going to be homework. So we're going to start this. But we'll start it together.
Okay.
So you should have this document that says Symmetry Definitions and Proofs. Can you see that? Can you see my screen? Okay. Now you should have that same document up. You don't have to worry about sharing your screens. Just getting this one up. And we're going to make transformational definitions for special triangles and special quadrilaterals. All right, so this is a new approach, not the usual definitions. So here's a symmetry definition for an isosceles triangle, a triangle with one line of symmetry. That's not the usual definition, okay? But that's going to be our definition. A triangle with one line of symmetry. All right? So the first part, A, says, why must the line of symmetry pass through a vertex? And the hint is make an indirect argument. It's nice if you have some paper and a pencil, I think, for this. But think about why the line of symmetry has to pass through a vertex. What would happen if it didn't?
You wouldn't get a line of symmetry?
We're assuming we have a line of symmetry, so I want to know what's wrong with it not passing through the vertex. We're assuming we have a triangle, it has a line of symmetry. Why does that line of symmetry have to pass through a vertex? What would happen if it didn't? And it really helps to draw a triangle. And what does a line of symmetry mean? Let's remind ourselves. What does a line of symmetry mean?
If you reflect about that line, you get the pre-image is the same as the image.
Good. Okay, so what would be wrong with a line of symmetry not passing through a vertex?
You wouldn't.
The vertex of the triangle wouldn't map to itself.
That's right. You wouldn't. Right? If it didn't pass through, then when you reflected it, you wouldn't have the same triangle and it couldn't match to itself. Make sense?
Yeah.
So that's what you want to write for A there. Now you can write it. You should save this document with your initials at the end, because this is your homework. So it's going to be to finish it. So when you open this document, you can write that and save it with your initials, and then that's your homework to send to me, okay? So you want to write something there. So I'll do it here. So if the line of symmetry didn't pass through, well, you guys write. If the line of symmetry didn't pass through the vertex, and it helps to draw this, then when you reflected, you wouldn't have a triangle anymore. Wouldn't match. And it has to be a triangle. All right, so given that the line of symmetry passes through the vertex, I'm going to open GeoGebra and make this. So we can see it. And I got 4 more minutes, but that's okay. So what I'm going to do to make my isosceles triangle is make a, I think I can just make a circle here. Yeah. All right, so there's a circle. And I'm going to make 2 segments. So I'm going to make my isosceles triangle. 1, here.
Triangle.jpg.
And actually, I'm going to make a line. I have a better idea. I'm going to make a vertical line as close to vertical as I can because I want there's a vertical line. And now I'm going to complete my triangle by reflecting because that's kind of the deal. So I'm going to take reflect, yes. So the reflection tool, this around this, across this line, there's the other side. And now I do a segment again. And here's my isosceles triangle with my line of symmetry. And I can move it, if I did this right. This is a dynamic isosceles triangle. Yeah. Okay, it could be like this, could be like this. Fair enough. So here's my isosceles triangle. And the next question was, what properties of that triangle have to be true given that this is a line of symmetry? So I'm going to label. So that's A prime, A or A prime, that's C, and that's whatever it is. Okay, C and C prime. I could change them, but I don't want to because we're almost out of time. So ACC prime, that triangle. What's true? Oh, and I want to name this point in the middle here too. There's a point, and I want to show you later. That's E. All right. So what has to be true of this triangle? And the answer is lots. Just knowing that that's a line of symmetry. What has to be true? Give me some stuff.
C and C prime are equidistant from A, so then AC and prime A prime are the same length.
Yeah. Say that again. What are the same length?
AC and AC prime.
Yeah. Right. So two sides are equal. That's right. Two sides of the triangle are equal. The usual definition. What else? Walter, chime in because we're almost out of time.
Oh, the line of symmetry is the perpendicular bisector of CC prime.
That's right. So the altitude is the perpendicular bisector of the triangle. The altitude to the base is the same as the perpendicular bisector. So we have all that all in one shot. And what else? Last thing.
Angle A prime CC prime is congruent to angle A prime CC prime.
Right. The base angles are equal. We get everything at once without doing, special proofs. They all just comes out of the definition. Once we know that's a line of symmetry, we get everything you want to know about an isosceles triangle. Okay. So that's a start. And the homework is going to be 1 through 3 of this and some other stuff. So I think you'll be able to, with that start, you'll be able to do it. And I'll just encourage you one more time to consult with each other. That's a good thing to do. Send an email to the other two guys and say, I'm not sure why this is true. What do you think? Okay. Your time's valuable, and I don't want to take any more of it. So, okay. We're done. We're done for today. And, boy, you had a heavy math day today, so relax.
Yeah.
Take care, guys.
Bye.
Thanks. Bye.